Hey guys, good morning. Frank Victorine here. So the topic today, and I think this will be mostly focused around two-stroke engines, but the reality is it'll work on four-stroke engines. Most of the theories should work on RC car nitro engines. I'm trying to decide how many different topics of fuel I'm going to cover, but let me first cover the bullet points that I've outlined here. So the way that I've labeled this is understanding the correlation between engine compression, ignition timing, and octane of fuel. And then I may have a brief discussion on combustion chamber shape and design of combustion chambers. And I think you could spend an entire day just talking about the different shape of combustion chambers, wedge shape, spherical combustion chambers, different angles that are designed to change how the fuel, as it propagates or as it burns, the expansion rate of the fuels, how that goes along with combustion chamber shape. So there's just like any of this stuff, it's like, man, there is just a mountain of engineering. So with that said, I'm going to go ahead and jump in here and just start talking about this. So the first question that I think I'd like folks to think about: why does an engine need compression? Will an engine run without compression? Well, and the answer is that we all know, or at least the vast majority of us know, that an engine that has low compression or no compression, the engine physically won't run. You can't get it started, and it's like, okay, that's important to know. But then it brings us into the deeper question: why does an engine actually need compression? And so if I take gasoline, right? Well, a few different examples is that, to start with, let's say, for example, that I've got my gas jug, right? And I've got some gasoline in it. And then let's say that I've got an opening in my jug. And then I take a match and I light the match where the match is on fire, and I drop it down into the gas jug. Will it catch on fire? Probably not. So if I have a whole bunch of gas fumes, and if the gas fumes contain oxygen, right, which would mean that they're in our atmosphere, that gasoline has to react with oxygen in order to burn. So if I have, and this is where you get to this whole 14.7 to 1. And basically what that means, 14.7 to 1, that's one part of fuel, and that's 14.7 parts of air to have the optimum air-fuel ratio for the sweetest burn rate, right? That's where fuel burns the most complete. It propagates the best. So again, if I were to take this match, light it, drop it down into the gasoline, well, if the match reacted, if this burnt match reacted with the oxygen and some of the fumes that were coming off of the gasoline, oh, you've got a problem. You've got a serious problem. But let's say, for example, somehow I could light the match inside the gasoline, right? And maybe not a match, but something else. Would the gasoline catch on fire? And the answer is absolutely not. There's no oxygen. So that, in the broad scheme of things, really starts to paint the landscape of how combustion engines work, the reason that you pull in a certain amount of air relative to the amount of fuel. So from here, so we know that if we take gasoline, we have something between, I'm just going to give you some ratios, 8 to 1 up to about 20 to 1, right? This is really rich. This is really lean. This thing's going to burn. And if we're somewhere in the neighborhood of about 14.7 to 1, this thing's going to burn near or at its optimum rate. In other words, for the amount of fuel that's being provided, it will generate the greatest amount of heat energy. So So you would think, knowing this, that you wouldn't even need compression. That you could just take an engine, get the air-fuel ratio, move the piston to top dead center, and maybe I should take a minute and talk about this as well, right? So let's and guys, once again, I didn't. This is basically ad lib. So I'm just talking about this stuff and drawing some of it out and trying to put it together in a way that it might make sense. So if I take an engine, right? So let's just say, for example, that I've got my cylinder here. That's my head. That's my cylinder. Here's our piston. We have air and fuel in here. And that if we're at 14.7, and then if we have a way to ignite the fuel, what happens is that the nitrogen gas inside of the fuel heats up and expands and pushes the piston down. So that's the thermal event. So all engines work on heat expansion. And so you figure, if we start to look at air and what's inside of air, and there are some inert gases, but the two big ones, we have somewhere in the neighborhood of about 70% nitrogen, and we have 20% oxygen. And that the oxygen reacts with the fuel and causes the nitrogen to expand under heat. And that the more heat we can produce, the greater the expansion rate, and the harder or the faster or the more force will be generated to push the piston down, right? So there's some thermal combustion physics of, what does this thing actually do? Works on heat, baby. So this leads us to the question: why does an engine need compression? So here's the interesting thing, that if this combustion chamber didn't have any compression ratio, what would happen is that if we were to compare, we'll say that we've got a box full of just loose air, right? The molecules are real far apart. We've got some air, we've got some fuel, we ignite it, and it expands. But what do you think happens if I were to compress it, right? Because air is compressible, and get the molecules where they were much, much, much tighter. We'll say we compress it all the way down to here, and boy, we could get into Boyle's law, Bernoulli's law, and Venturi's law, and there's a ton of laws based on gases that were studied between the 14th and 17th century, somewhere right in there, 18th century, depending on, right? So this stuff goes a long ways back. We've been, mankind, we've been studying the correlation of gases and what they do. That was before a lot of these other technologies were developed. So what happens here, to stay on topic, that once we compress this air-fuel mixture into a tighter spot, now what happens is that the rate, because if you look at this, they can only expand so far. And the other problem is the molecules are so far apart, not all of it will burn efficiently. But if you start to compress it where all the molecules are close together, and then you ignite it, all of this is going to propagate. And the term propagation is really pretty simple, that you would probably imagine fuel burning instantaneously, but that's not what actually happens. That if I were to ignite it with a flame right here, what's going to happen is that this molecule is going to react with this molecule, and this molecule is going to react with this molecule, and it's going to expand. and the whole thing is just going to, if you think about, if you take a paper towel and light it, it doesn't all go up in fire at once. You usually light up this little bitty corner, and then what happens is it expands from there, doesn't it? Right? So that's what now. So is there a point of diminishing returns? So there's a price to be paid, because what happens is that as I start to move the piston up and I generate pressure, right? So we are literally putting pressure on the cylinder, on the gases. You put more pressure on it. When it blows up, it's more violent. You put more pressure on it, it blows up where it's even more violent. But there's a point of diminishing returns where you exert so much pressure on the fuel that it can't overcome the force that was initially applied to it. And then what happens is that, like anything, there's a bell curve. There's a sweet spot. So tuning an engine, that compression ratio plays a very large part for tuning optimum cylinder pressure. And that, if I could take a compression gauge, stick it inside of this thing, and start measuring cylinder pressure, and by the way, they have some math that drives all this stuff. The term is called BMEP, right? And I'm just giving you the acronym here. That's brake mean effective pressure. That's the mean pressure. It's the mean pressure inside of the cylinder at all events. And most engines that are running on pump gas, boy, and I say that, usually will have, we'll say 3,000 on the real low side. A really high state of tune engine may have 6,000 pounds of mean pressure inside of the cylinder. So that's pretty simple to see. That an engine with 8.5 1 to compression ratio isn't going to make as much power as something that's got 13 to 1 compression ratio. But the one with 13 to 1 compression ratio, you probably can't put pump gas in that real easy, right? Okay, so I think that should cover some of the basic laws of physics of how combustion engines work. So to recap this, expanding nitrogen gases, you need an air-fuel ratio of 14.7 parts to 1. The 14's the air, right? You need more air than you have fuel. And by the way, that's by weight. That's not by volume. Okay. So I hope that answers the question on why an engine needs compression. And that we also realize that when we start to look at some of the basic physics here, that there's very likely a point of diminishing returns, that you can have an engine that has